for week 3. So this was about overbooking, and the corollary is estimating the number of no-shows, and how we do this with respect to our knowledge of area under the curve and so forth. So I would suggest that we begin with developing a problem statement. But before we do that, what are we trying to measure? What problem are we trying to solve? And whatever question we ask, it needs to be one that we can answer empirically, that is through observation, and in such a way to quantify our results so that we can perform some numeric calculations. So before we get started with that, what must we know? Well, we need to know how to compute a z-score, and that's what you were reading about in the assignment for this week. And there were several exercises in the book, and no doubt that you found some online about how to compute the area under a normal curve associated with a particular z-score. So, you would need to know what I'm calling a situational awareness of the standard normal curve, standard deviation, z-scores, means, and all of that with respect to the type of the problem statement. And I think there are 3 kinds of problem statements when it comes to computing areas under the curve. And that would be the area above, or the area below, or the area between. So once you have all of that kind of procedural information and the numerical information, you have to integrate that into the context of the problem. So the first thing that you would do is to define the population. And it probably would not be all aircraft in any airport in the world at any time period in the world. You need to more narrowly define the population. So, there are seasonal averages. There are different routes that probably are more profitable than others in terms of the fill to capacity. And then maybe there are some individual differences among aircraft. And you could probably think of a lot of other different classifications of a population in order to narrow it down to a point where we can study it, and then we can infer our results back to that population. So after we have identified the population, then we need to identify a sampling method. And in any type of a situation where you're going to draw a sample and then make an inference from that sample to the population, you need to have some form of a random sampling method. And it could be some type of a stratification. So maybe it could be stratified in terms of time of day, or length of the trip, or however you want to disaggregate it. And then, as I pointed out earlier, are there some seasonality issues, routes that have to be taken into consideration, different type of aircraft, and so forth. So you identify the population, you draw a sample, and then we can take information from individual aircraft in order to create a sample. After we have drawn the sample, then we're going to take those data and compute a frequency distribution, which is a visual representation of the data. And then we're going to compute the descriptive statistics or the numerical representation. So I just made up some numbers here. In this situation, we drew a sample of 100 scores or 100 different situations of no-shows for particular aircraft on a particular route at a particular time of the year. And we computed the mean of 6 and a standard deviation of 2. So that's what describes that distribution of scores. And then we have to come up with a decision criteria. So we see that on average there are 6 passengers who do not show up for a particular flight. But we also have to take into consideration the entire distribution of no-shows, including the knowledge of the variability within that distribution. Because if the variability is very small, then we'll have a very peaked distribution, and that would affect the point at which 95% of the area under the curve might fall. We'll go with the mean of 6 and a standard deviation of 2, and I just popped this into one of the applets, and I said I want to know where 95% of the area under that curve falls below, and it would be at 9.2897 people, so you'd have to kind of round that down. We can be 95% confident that the number of no-shows will be less than 9.3 customers. Therefore, if the risk level is 5%, then it would be okay to overbook up to 9 customers. And if we overbook by more than 9 customers, then we're going to run the risk of overbooking a flight, and 1 or more passengers will be rebooked on a later flight. Now, that said, we could just overbook by 5, and still we could run into a situation where for a particular flight, we may have more people that show up for that flight. There may be fewer than 6 no-shows. So remember that we're just inferring in general back to a population. We cannot specify that it's going to be accurate for every flight out there. So in conclusion, we probably need to do an evaluation. What would be the effects of changing our level of risk? So if we wanted to be 90% sure, what effect does that have? If we wanted to be 99% sure, what effect does that have? And who's making these decisions? And if it is finance, and they're wanting to be sure that every flight is packed to capacity, then they're probably going to want to be, like 99.99999% sure. So we're going to include just about everybody, and then, of course, they're going to run the risk. There are going to be some unhappy passengers, depending on a particular aircraft. What is the cost of being wrong? That is, what happens if you set your threshold at 95% and all of a sudden you have a situation where you had overbooked by 8, but in fact everybody showed up for that flight, and here you had 8 people that you had overbooked. What is the cost in many ways? Financial cost, customer relationship cost, and all kinds of things. So there are cost-benefit curves out there, and people in analytics in your finance department probably know them very well. Um, and they also come up with their own thinking about establishing risks. And I know from an academic perspective, when we're dealing with finance, they are a little more ambitious than academics are. So there's always a lot of opportunity for further discussion. And then finally, what problems arise with any type of sampling method. So remember that when you draw a sample, you assume that it's going to be a random sample. Well, is it really? Do we really have the opportunities to draw purely random samples? We do, but there are costs associated with really good methodology. So this is my solution to the problem, and I'll be looking forward to reading yours. Thank you.